very good pronunciation of our names. I think it's the first time someone pronounced them correctly. Maybe
Yeah.
the fact that you're Italian has something to do with it. So, hello everybody. We're honored to be here at this anniversary edition of Hack in the Box. We're extremely jet lagged because we arrived yesterday at midnight, so I apologize in advance if we will talk nonsense throughout the talk, as usual, but more than usual this time, so, you know, could be really a problem. So we're going to talk. I'm Andres, Daniele. Say hi, okay, good. He's more jet lagged than me, okay, so he takes the blame. So we're going to talk about practical exploitation of embedded system, which is a way for us to do a talk about a few challenges that we thought are interesting when hacking embedded systems and the way to approach them. And at the end, we will feature an example of such hack against a certain Apple device. So embedded systems. So we have a lot of slides, so we'll try to go through fast. There's lots of content. So what does it mean, an embedded system? So embedded system, the definition is a system which is part of a more complex system, and it is designed to do a very, very specific function. For instance, all of you know examples of embedded system. A network router is a device which has a very specific purpose. So it's not like a general PC, a general computer, so it is referred to as an embedded system. A printer could be an embedded system. A point-of-sale device. Smart cards are considered an embedded system. Automotive equipment, we talked about in the past, our embedded system, avionics, and so on. Also, if you have an Ethernet card on your laptop and it has its own firmware, that is also considered to be an embedded system. System management controllers, all peripheral controllers, and so on. And these embedded systems, they can be just microcontrollers with more or less advanced functionality and tiny firmware. So, or they can also be more complex systems with full real-time OSs, such as VxWorks, ThreadX, and other systems. So it's a very, it's a very large area, very complex area. There are, several points to make. So the talk that we're gonna make focuses on a few specific issues that we thought are interesting, because of course this field has been discussed, to great length before, and there are many, many presentations about exploiting embedded system. So we try to show you about a few specific items which we think are very unusual. They might have also an historical value, and that we think are interesting to discuss.
So yeah, one of the first things that usually we do when we start hacking an embedded system is, we are starting looking for some debugging or console interface into the embedded. And the vast majority of the embedded systems, usually they expose interfaces like, serial interfaces like RS-232 in this case, or JTAG ports or similar. In the case of serial interface, it's very easy to use those kind of interface, and it's very easy to find out eventually the pinout of the interface itself, in the case you don't have any documentation of the interface. With the JTAG, things can be more complex, especially the procedure of finding out the interface pinout can be very complex and time-consuming. And board manufacturers, vendors can be sometimes they can implement hardware protections or software protections. By hardware protection, I mean zero-ohm resistors or barn-fused, or every protection that makes the JTAG interface not operating at all. So you need to actually desolder or solder resistors on the board. So you need to perform an electrical analysis of the board and understand what you need to do before starting actually using the JTAG interface itself. By software protection, I mean sometimes the vendor can pretend a custom initialization sequence then can be very complex in terms of timing. By initialization sequence, I mean that you have to perform some sequence, some electrical sequence against the JTAG interface. So, for instance, I don't know, you have to keep high one pin for, I don't know, 2 milliseconds, and after that you can actually use the JTAG port. So as said, for serial interface, it's very easy, and the process of discovering the pinout is straightforward. You have just to connect. Usually, we use a logical analyzer. You can just do this ignorant approach. You can just connect every pin of the exposed by the interface to the logical analyzer. You start to your sniffer. You start sniffing all the change in the signals that you are monitoring. You reboot your target device because, of course, you know, during the boot procedure, the device usually it leaks some data on the serial console, and of course, at this point, we wait for some data coming out to one of the pins that we are monitoring. At that time, this will be, you know, a good TX candidate. At this point, it's very important to be able to estimate all the serial parameters. This is usually very easy. So we just have to estimate the baud rate, looking at the timing of the signal. We just to estimate the data bit, the stop bit, the parity, and of course the bit order. The other thing that can be really bit annoying is to understand the logic, because sometimes we have a serial interface that works with inverted logic. That means that we need to add a NOT circuit before or after the serial interface. And of course, as far as we know the TX, we can try to brute force for the RX, looking at some feedback on the previously founded TX. And that's pretty simple. Here we have an example of a logical analyzer connected to all the pins exposed by this interface. And yeah, at some point, rebooting the device, we can see that there is some data coming out from the interface. It's a jumping space to a space something else. And yeah, and here we have a picture of a very simple circuit that it's used sometimes. So depending by the voltage of the serial interface, we maybe need some voltage conversion before actually going to our PC or to some serial to USB converter. We need to perform a voltage conversion from TTL from 5 volts to minus 12, plus 12 volts. But yeah. And that's it for the serial interface. So as said, for the JTAG, things can be more complicated. And that's because JTAG interface, it's not fully standardized in terms of number and position of the pins in the interface. So every vendor can do basically whatever he wants. And the other important thing to understand is that sometimes founding the JTAG port is not so interesting, because also the features that can be implemented through this interface is something that it's vendor dependent, and some vendor just put the JTAG port for boundary scan feature. What does it mean? It means that with those JTAG ports, we can just perform some electrical test to see if the connection between the different integrated circuits on the JTAG chain are properly connected or not. The other feature that it's more interesting when you are hacking some embedded device is the in-circuit debugging feature. It means that through the JTAG port, you can perform more advanced operations against the CPU, like CPU single stepping, breakpointing, and having full access to the read-write, access to the system memory, passing through the JTAG. Scanning the JTAG, so the process of finding the pin out of the JTAG interface, it's more complicated to the serial interface. JTAG ports can sometimes expose a large number of pins, but we have to focus our attention only to this set of pins. So we are focusing our attention only to test data in, test data out, test clock, and test mode select. And of course, okay, we have also to keep in mind that it can be a test reset pin that we need to keep it high in order to protect the entire logic, to protect the reset of the entire logic. And of course, also VCC and ground, they are also interesting. So first thing, we start finding the ground. That's easy because we just usually using a multimeter, we can check for short circuit in the board. So knowing where the ground is located in some point of the board, we can estimate the position of the ground pin in the JTAG interface. After doing this, we have to estimate the VCC, because we have to keep the VCC and the ground outside the range of the pin that we want to logically scan. And to find the VCC, we can use this technique. It's fairly easy and it works. We can just use a probe resistor, something around, I don't know, few hundred ohms. It really depends by the voltage of the JTAG interface you are working with. If the interface is working with 5 volts, it will be safe to use a 500 ohms, because the idea behind this is that we want to keep the current above something like 10 milliamperes. And if you are working with an interface working with 3 volts, you can just use a 300 ohms resistor. And what we do is basically we try to pull down every single pin in the JTAG port, and when we found some pin that it's not easily, it cannot be easily pulled down with the 500 ohm resistor, it means that it will be a good VCC candidate. So at this time we have VCC and we have ground, so we can start actually, you can start to actually perform a scan against all the pins in the JTAG port in order to find this set of pins. So the scanning tool that we are going to use, it has to be this feature. It has to be to present a large number of GPIOs. This is very useful, especially when you are scanning big JTAG port with a large number of pins. We don't want to manually move connectors during the scan procedure, and that's why we are looking for some device with a lot of GPIOs. The I/O speed is not relevant during the JTAG scanning process because it's something that is controlled by with the T clock, with the test clock signal. So it can be controlled by the scanning device. And yeah, microcontrollers are the perfect tool for doing this job, because they have a large number of GPIOs and they are fast enough to do the job. So here in these slides, there is the top state machine. What is the top? The top controller is a 16 stage state machine that basically controls all the logic inside the JTAG of the integrated circuit. And so we have 3 different scanning strategies. They are all based on the same concept. Basically, the idea is that we push a logical pattern 1, 0, 1, 0, and so on in the TDI, in the test data in pin. We control the clock, so we raise and we make a rising edge, and the falling edge on the test clock, and we go to look for some data coming out to the data out, and we can of course we can estimate if this pattern is the same that we have pushed into the TDI or not. The choice of the scanning strategy really depends by which is the command, which is the default command that it's implemented by the vendor in that specific JTAG. So sometimes sometimes the default command is the bypass instruction. Something else it can be the ID code. Yeah, I will just stop here talking about the JTAG scanning, because if you are interested into this topic, we can just maybe you can just ask after, and we can show you a little bit more examples and other things. But yeah, it's as I said, it can be very complicated depending by what the vendor did with their device. The other thing that it's very important when we starting hacking an embedded system is, we first of all we usually are interested into having the firmware of the device itself, and a lot of time the firmware itself is stored in dedicated flash memories, and usually nowadays these flash memories are speaking two main protocols, SPI and I2C. Or yeah, well, SM bus, it's the same. It's I2C at the end. And here, vendors can also implement some sort of restrictions, some sort of access control process. And sometimes, in order to be able to have full read-write access to the memories, we have to physically remove those memories to physically desolder the memory, the chip, from the board, because otherwise from the OS it's impossible to bypass the vendor restriction. And so yeah, this is an example, an horrible solder head. This is an SPI memory desoldered from the board, and in this way, using tools like the FTD module, or this module here, it's an SPI to Ethernet converter, XT Nano it's called. As you can see, they are very, very small. This is an RJ45 connector. This is a mini USB connector, just to make you an idea of the dimension of this thing. And you have various solutions here in order to be able to read the data from the memory. You can use a custom programmed microcontroller. We have an example here. I'm not going to show it because I have to be quick. And so using microcontrollers, it's quite easy to perform, to make a bridge between the SPI interface of the memory and modules like the XT Nano, for instance. So you can send the data from the SPI channel of the memory to a TCP IP stream. Or you can use tools like FlashROM. FlashROM is compatible with the FTD with this module, or you can use other SPI to I2C converters like the XT Nano.
Okay.
So yeah, I think.
So you did good considering the jet lag.
Yeah, I tried to be quick.
You were understandable.
Yeah.
So we mentioned, of course, that that sometimes you might need to read the actual physical memory for getting the firmware. Of course, eventually one of the things you want to do when you want to exploit system, especially if you also have an update in your hands and you want to try to modify that in order to push it to your device, is you got to understand what kind of checksum algorithm is being implemented, because of course if you mess with the firmware, if you change it, then the checksum will not match. And this sometimes can be trivial, can be extremely easy, and sometimes can be quite complicated and quite boring and tedious to do. Of course, the good news is that in this area, still nowadays, I would say the 95% of all the embedded firmwares on the system we talk about, you don't have any security protection, no signature verification. You might have elaborate checksums in place, but they're mostly for integrity reasons and not for security reasons, even if sometimes they're used for security in the way that as you don't know the algorithm, it's obfuscated to you, then they think it is a security measure. And this is very common. I mean, every time we approach one of these systems, this is how it is. So when you have a firmware and you are disassembling the code and you want to understand what kind of checksum algorithm is used, most of the times we're talking about CRC42 or variants. And of course, one of the main things that you should look for is the polynomial, which is used for doing a computation. So if you find this string, or rather, if you find the reverse representation of this polynomial, which is the standard one using CRC42, so if you find this string, you will know, for sure, unless, there's a chance that opcodes are used for something else, that you're dealing with a CRC42. But there are some exceptions to this rule, which we think are worth discussing. So first of all, once you identify the polynomial, once you try to figure out what algorithms we're talking about, there's one very good, important thing to keep in mind, is that most CRC algorithms, they can identify following what's called as the Rocksoft model. So the Rocksoft model specify standard parameters that can be tuned, that can be changed, applied to a standard algorithm, and from there you can reproduce all the different flavors of checksum algorithms. So for instance, if you want to have the display represent CRC16, CRC32, the POSIX variant, or standard CRC42, or GEM CRC, which is a variant of CRC, we can always do that by representing these parameters. So the polynomial, which is what's used for generating the CRC, we have an initialization vector. We have parameters which tell us how the different bytes are treated into different stages. And we have a value which is XORed to the final output. And then there's also a check, which is the checksum of the ASCII string 1, 2, 3, 4, 5, 6, 7, 8, 9, which is very useful when you want to compare and understand which kind of algorithm you're discussing about. And so, for instance, even if you find the polynomial which is related to CRC42, it might not be standard CRC42. For instance, GEM CRC, it's a variant of CRC42, which differs also for the XOR out check and these two Booleans, and it leads to completely different results. And you might be fooled by the fact that you will find that polynomial, and you might be sure that it's standard CRC42 being used, and then you might not realize that instead it's GEM CRC because it's a different flavor. And once you know these changes, in the different protocols, then you know what to look for in the assembly, and you understand exactly which kind of algorithm we're discussing about. However, the problem is that not every CRC flavors can be parameterized with the Rocksoft model, which leads to more interesting problems. So, for instance, this is the Ruby code which shows how to generate a table for the CRC2 applications. A table is a way to cache, to pre-compute a specific step of the CRC algorithm to defining in a table, which is then used for lookup when you perform the checksum computation. The reason why this is done is purely for performance. And this is also very important because you can also find the table, of course, in your firmware code. And knowing which table is present, of course, can also lead you to understanding exactly what kind of algorithm is being implemented. So this generates a table using the reverse polynomial for a specific algorithm. The polynomial here is the only different criteria for generating the table. And this is the algorithm generation. So the example shown here is by using the table. So the table is being generated and is being looked up here for a specific index, which relates to the positional entry in the table. The table has 256 entries. Or otherwise, you can apply the polynomial manually every single time. And again, this is more time-consuming than this. And we show both ways of doing it. And this follows the Rocksoft model. So we have the initialization vector, we have a XOR out value, we have the polynomial, and so However, there's one flavor of CRC, or more than one, which it is CRC. It was specified in a draft version of POSIX, so not standard POSIX, but it's draft 11 in this case. And it cannot be parameterized via the Rocksoft model, but nonetheless, you will find it in code out there. And so first of all, we can see that the table differs. So this is the polynomial which is being used, which is one of the standard ones I've shown you before. But there's an exception. If the index is 0, we have this value here. So that's one of the different things that you have in the table. And if we see the actual algorithm, this is the version with the table, we see that this protocol has an exception that if the index is 0, then you don't have the standard lookup for the table, but you replace the index with a value which you're keeping track for every time you found a 0 as an index. And this difference make it so that the algorithm cannot be parameterized by the Rocksoft model, because even if we are dealing with the same parameters, the actual core algorithm is slightly different. And it's slightly different in a way which will make your life much more complicated when you try to understand why this is not CRC42. And so, but if you know that this is the case, then it's easy to spot that in the assembly code, in retrospect. But this is one very tricky example. And this is the same without the table. Again, we have the exception here. And one of the reasons why this algorithm is being used today is because there is some code out there which refers to it not very clearly. It mentions that it's standard CRC42, and some vendors, they're picking it up. So for instance, we can have, in the wild, you can find the draft 9 version of the standard, draft 11 or the draft 12, and they all lead to different results at the end. And these are not parameterized by the Rocksoft model, opposed to the standard POSIX algorithm or the CRC42, which is commonly used nowadays by PKZip or by also the Ethernet. The Ethernet packets at the link layer, you have CRC computation being performed with this algorithm. So we think this is an interesting thing, which is not cannot be easily found on the web. It's not, so we thought that it was relevant to discuss it, and it's one of the challenges that you have when trying to upload an arbitrary firmware. Of course, also, if you know which algorithm is being applied, one of the things that you can also do, of course, if you want to try to match the checksum rather than try to rebuild your own, you can also try to find collisions. There are a few tools out there which allows you, if you have 4 arbitrary bytes of freedom in the payload you're trying to create a checksum for, you can find a way to create a payload which matches a known checksum as long as you have at least 4 bytes that you can arbitrarily control, which is often the case. So that's, knowing the algorithm and knowing that, you can also, don't bother about changing the firmware, changing the checksum. Suppose that the checksum is somehow hard-coded somewhere else in the code and you don't have access to that. You can have your payload colliding with that checksum. So you can make your changes and still have an output which will produce the same checksum of the original payload. But of course, you need the algorithm, the proper algorithm to find that. So that was one thing. Next thing, it might be that you don't have the firmware, or the firmware cannot be easily reverse engineered, but via means of the previous access that has been discussed, you actually have access to the system. So you can be on the system, and you can copy your binaries, and you can execute your binaries. Or sometimes you are in an operating system which allows you to have kernel modules, which is extremely common. Or you can modify the binary itself and inject code. And suppose you want to debug or you want to reverse engineer some specific custom driver which is embedded in a kernel, which is not easily exposed to the user space, and that the system uses to access some kind of privileged information. So cryptographic key exchange, or talking to some other device which is on board. And most of the time this is the case. This is real life scenarios. You have embedded system with specific drivers included in the kernel, and they're not exposed at all to the user space of the embedded system. Also because the user space on embedded system, it's not something that is used because you don't log onto the system. So you have the OS, and little attention is paid to the kind of access that is given to the user space. So it might be really, really hard to understand what's going on, even if the code is inside the kernel. So what you can do, and this is, it's fun to do, and it can be straightforward, it can be tricky, but it's very rewarding when you do it. You can patch the kernel, either a runtime if you have ways to have modules, or you can patch the binary, upload it, and then put debugging helper within the code that allow you to understand how some specific function works without having to reverse engineer them all. So, of course, even if we are in 2012, most embedded systems, real-time embedded systems, they give you dev-mem, and you can write and read from it. Which means that if you want to hijack a function, you just need to have the function pointer of the function you want to hijack. You need a new function pointer or a function which somehow you injected in kernel memory, or either via the firmware update or because your module is having that. And you can open dev-mem, you seek to the pointer, and then you replace the pointer with your new one. It's very easy to do. And you can also do it even if you don't have the OS development toolkit. This is really important. In real-time OSs especially, you have standard shared objects which are loaded as kernel modules, and they have a little overhead with descriptors of how the module is loaded. And if you can grab one of those, which are usually present on the file system on the flash, you can modify them and then have your own code within the module. And you can also load this without having to access dev-mem. And I'm going to explain why you don't need the OS development toolkit, which is anyway available in most cases, but this is important. So this is one example of how you hijack a function. So you define a wrapping function, which is going to be shown in the next slide. And so in that way, you have a pointer to it in kernel memory. So that's your function. Then, depending on what kind of architecture you're dealing with, you create a jump. You create the assembly opcode for the jump that you need for going to the address of that function. So here, this is MIPS. In this case, the result of this is the proper opcode for jumping to that function pointer. You create a placeholder, which is just a character array for the original function, because you don't want to mess up with the functionality of the system. You want to wrap existing functions in a way that you don't affect their behavior, because if you affect their behavior, then of course you have nothing to debug. And then you can define a prototype for the function you want to inspect and point it to the address of the function holder. And this will allow you to return back to the function which you're holding. So in this case, we're using C just as a graphical user interface to assembly, okay? It's just for making things more simple. And if you don't have the OS development toolkit, so you don't have the symbols results for the function that you might need, it's usually very easy to find them within the kernel code, because you can always identify the system call table. And the system call table, the ordering of the syscalls, 90% of the cases, it respects the standard ordering of the syscall numbers for the flavor for which that OS is derived from. So most of the times BSD, sometimes it can be Linux. So if you know the pointer to the memcopy system call, for instance, you know the pointer, you can just define a prototype for that, and this will allow you to access that function by writing C code. You don't mess with assembly too much, and you don't need the development toolkit for doing that. You just need a compiler for the specific CPU architecture. And what you can do, you copy the existing function in a placeholder, so you keep it there. You replace the function pointer with your own pointer to your own debugging function. And the debugging function, the interesting thing, so you don't need to have the exact number of arguments of the existing function, because the way the stack is handled, it will still work. You will still not break the system. If you place 15 arguments here, you're always safe. You put your custom code just for, you can print somewhere, some OSs, they have a special version of printf, which prints to the serial console, for instance, which is really handy. So you can print the content, the pointers which you're getting. You can also decide to follow them if you want, and then you just call back the original function. So for instance, if you have one specific driver which is talking to a chip, which is exchanging cryptographic keys on the system, and you don't understand how that works by reverse engineering the US, if you wrap the function and you display the arguments in this way, you will intercept the key without affecting the functioning code. And then, of course, once you do that, of course, other than debugging here, you can also have your custom code. So if you want to lie about a specific arguments which are being passed through the system, if you want to intercept them and change them, that is all quite easy to do. And you can also do it without US development toolkit. So it's quite cool. And to get as I mentioned before, the syscall table, the syscall table is fairly easy to look up in a kernel image or in memory, because it's a very long list of pointers which are very close to each other. So, and once you add them, they're always in order. So you have a system called 0, 1, 2, 3, 4, 5, and so on. And then you can reflect to the ordering for the OS family. Or if you have a binary on the system and you know what the binary is performing, like ls, of course you can also try and look, depending on where it's linked, or you can look in a standard library, but it can be easy to infer the pointer of this function. Of course, with easy, I say that it still takes some time, but it's quite doable. It's quite possible to do this kind of kernel patching completely blind in relation to the OS you're targeting, and we think it's a pretty nice approach. So, how much time do we have? Okay, we're good. And of course, if you have questions about all of these, we can show you examples later. You can approach us. It's good fun. So we discuss how to access I/O ports. We discuss how to verify. We didn't approach, of course, the whole topic because that would take many hours. But we discussed a few interesting bits about checks and validation, and we discussed the kernel patching bit. So let's do a practical example. So the example we picked just for educational reasons here, but it's interesting because we haven't seen it released anywhere, is attacking the Apple SMC, which is considered an internal embedded subsystem, which is present on all Intel-based Apple laptops. So the SMC is the system management controller. It's an embedded microcontroller which you can also find on other systems, like on my ThinkPad laptop, for instance. It's very common. And usually you can play two roles. It can act as the system management controller, or the keyboard controller, or both. So when it acts as a keyboard controller, when you have the matrix count of the keyboard, it is being handled by this chip. And so why it is interesting, because Apple allows the firmware upgrade for this SMC. And so we show, how you can investigate and how you can flash arbitrary firmwares. And, it's an easy, straightforward, and nice process to do. So the SMC is generally used for several reasons, as mainly thermal management, the monitoring of the power, the management of the battery on the system. It can be used as a SPI bridge, which allows you to store some data not in the BIOS, but on a custom flash. Provides the ACPI OS interface. It can also provide buffering and buffering of some signals, and also level shifting if you need to talk to components which have different voltage levels. So it's convenient, and it's completely custom programmable functionality. So it's not that you buy it and it operates. You need to program it. So on Apple system, it doesn't manage the keyboard. It just manages the power-related keys on the system. And it manages the display lead open-close activity, the sudden motion sensor, the ambient light sensing, the keyboard light, indicator lights, the battery, and so on. So it's a fairly important piece of equipment that you have there. It can be queried, this is interesting, it can be queried by the OS, so it has a clear and, I would say, published way of interacting from user space with the chip. So you can retrieve what are called the SMC keys from the chip, or you can write to them. And these keys, they give you information about the light activity, the battery status, if it's present or charging, and so on. You get that from the SMC. You get the RPMs. And you can set the RPMs of the different fans. There's a Ninja action timer, which I have no idea what it is. Maybe someone which is expert in Apple can tell me what the Ninja action timer is. I like to think that when you set that, a Ninja pops up and kills you. I think that would be quite awesome. You can get the current, the voltage, and so on of the CPU. This is just a subset of the attributes. There are many more. The motion sensor configuration register, and so on. All kind of things. So the update file, you get a DMG from Apple, which can be mounted. You can do all of this on Linux. It doesn't matter where you do it. You don't need to be on Mac OS X. You get a gzip compressed CPIO archive named payload, which contains some interesting files. So one, you get an EFI binary, and you get 2 SMC files, which actually contain the firmware. So the EFI binary is a universal EFI binary, so which means it's a binary designed to be launched in a pre-boot stage at the boot stage, pre-boot stage, in what's the BIOS of your Apple laptop, which is their own version of the EFI. So now you listen about UFI a lot, so Apple uses their own variant. They don't use UFI, but still this is a universal EFI binary for 32 bits and 64 bits, even if I don't think Apple has any 32-bit devices. Anyway, so this binary is blessed. So with the bless command by your automatic installer for execution at the first boot. And as an argument, it takes the firmwares, depending on the part number of your laptop. So the firmware, of course, are checked for integrity by the Flasher application. And, we wanted to know how this integrity check is being performed. So this is the file. It's been cut down for brevity, of course. So in the file, you have this series of strings, and then at some point, the data begins. So once we looked at it, it looked fairly familiar, but it's not a standard format, but it's very close to several standards, but it has its own peculiarities. So first of all, the H here means hash data. The S, this is our interpretation of it anyway, the security data, and D contains the actual data block. So this seems to be some kind of validation data. So probably the checksum information is here, and then you actually have the data of the firmware. So this, of course, it's very easy to spot, relates to the length. So 20, you have 20 bytes, 64, you have 64 bytes, and so on. And this seems to be a memory address of the actual, or anyway, an offset of the actual firmware which is being placed here. And the checksum, turns out it's quite easy. So if we see this line here, we see BF and then all zeros, and this value here is BF. 02, and this value here is 02. And of course, when we add data, the value is something different. But it turns out that it's very simple. It resembles a bit, it's not quite the same, but it resembles the SREC file format, and in some ways also the Intel Hex format. So the checksum is none other that there are at least 2 significant bytes of the sum of all the bytes contained within the data. So here we sum BF with all zeros, and of course the least significant byte is BF, and so on. So it's really straightforward to actually recalculate this value once you modify one of the data block. It's also easy to make it collide, because you know that at the end, only the sum has to match the checksum value. And the hash data here, the number of hash data sections is exactly like the number of the data sections. So each of these represent the sum of all the hashes for the data block. So hash data section considers the sum of the checksums of each 64 bytes of the data block, and the security data section, which is this one here, represent the sum of all the hash data sections. So it's like of a redundant checksum. You checksum, you check like a matryoshka. You checksum each individual data block, You have a checksum for the sum of the checksums, and then you have a checksum for the sum of the checksums of the checksums. So, and once you know this, it's pretty straightforward to modify. Actually, it's very trivial. You know, either by change it and then update the checksum, or if you want to find collisions. So that was the first step. The second step, we need to understand the architecture. So one of the things that you might try to deduce is that, you know, the first relevant data block begins, because before this it's not useful data, it begins at the offset 8,000, XF 8,000. We could speculate that 0, 0 here, so if this is an assembly representation, that these are probably knobs. So the knob code can be 0, 0 or 0, 0, 0, 0, depends on what the alignment is. So, but of course, when you deal with consumer products, you know, you go online and you find several pictures of the boards if you don't want to open your own laptop and break it apart. So you go to ifixit.com, you find a nice picture of the board, and you find this fellow here, which actually turns out to be a Renesas H8S 2117 family 60-bit microcomputer, which is specifically designed, or actually it is employed by several manufacturers as an SMC unit. So, you know, all chances point to this chip as being the actual recipient of the firmware we've seen. It's a fairly, I would say it's a very nice component, 16-bit architecture, 160 kilobytes of ROM, 8 kilobytes of RAM, and it has lots of I/O. Really, yeah, I2C, it has an analog to digital converter, it has a serial interface, and more than one actually. It has a keyboard buffer control and matrix scan. It's a low pin count interface, and it has a large number of generic I/O ports. And all of this you can read from the datasheet of the chip. And once you have the datasheet of the chip, of course you have the architecture, and you also have the instruction set. By matching the instruction set to the byte that you see in the firmware, you can easily see that 5A008986 is none other than a jump to an absolute address. So this represents a jump to offset 8986. And of course, you also have a GNU development toolkit for this. So you can also use a compiler for it. So the very dirty way of doing it, I mean, we just showed the raw material here. We're not fancy. We're not showing you IDA Pro and so on. We like you to show the bare bits. Then if you want to be more lead, then of course you can use all the other tools. So you cut out the data blocks which are interesting for you, and you convert the ASCII representation of the hexadecimal values to their actual binary value. So you do that with this one liner here. It converts the easily readable file to an actual binary, where you can do strings on it and you can disassemble it. Then if you have the H8300 development toolkit, which is available online, you point to the right start address, which is, in this case is offset X1000. You put the architecture, and you can disassemble the code, and we can see that it matches our expectation. The first instruction is a jump to X8986. So, and once you have this, of course, the great thing is you're dealing with assembly that is used in a microcontroller. So you get the data sheet, and the data sheet will tell you exactly what every register means. Before that, you need to understand where the data section is, of course, on the firmware. So there is a data section here. And for instance, these offsets here, they actually convert to strings. So this is a case statement where, depending on the state of a specific register which is looked up before, we reply to an SMC key query with different strings. And these strings are present in the binary, so we see that in this specific case, for this specific firmware, we just have a shift of X7000, so everything that you see in the code as reference, for instance, 1EAFE, you will find in the actual binary untouched in 17AFE. So once you know that there is this shift in the offset addressing between the text and the data section, which relates in how the binary is later placed into the address space of the microcontroller once loaded. But then once you know this, you can resolve all the different data related parameters, strings, values, whatever, which are present in the binary. And this greatly helps in understanding what the code is doing, or if you want to modify to return other strings in place of the one that is currently reported. And also, we discussed that the main functionality of this SMC to the user space is to set and give keys. You find all the keys within the binary, and you have this nice table which tell you the key name, the type of the key, and then you have some kind of offset here. And it turns out that, for instance, if you're asking for the key, which gives you the number of SMC keys which are configured in the system, we can see that this address straightforwardly points to the data section itself. So if we perform the same amount of shifting, the same calculation, we go back here, and this is exactly the value which is being returned when you query the SMC for the key command, which is the number of SMC keys, which is, in this case, 272. So immediately you have a way, if you want to don't be too fancy, to modify the static keys which are being returned, or to change dynamic keys to static keys, just by changing the offset here. Because this is the actual table which is used by the assembly code to do the lookup of the keys which are being asked over its interface. And also, if you relate the registers which are being addressed by the assembly to the datasheet, which now you have because you know what the architecture is, it's straightforward to disassemble things like this to the relevant I2C components. So if you look at the datasheet, for instance, you will see that FE88 is actually the register for the I2C bus control register of the second I2C port. And depending on the bits which are being cleared or set on that specific register, with the datasheet printed, you know exactly what happens here. So in this case, the device is setting slave addresses for talking to over the I2C. So once you have this knowledge, and once you have the datasheet of the microcontroller, you really can get deep into what exactly the unit is doing in terms of communication. And it might look complicated, but it's actually pretty straightforward once you are in this specific mindset. And this is another example here. For instance, this is the battery, the maximum number of supported battery, which is addressed here. And for instance, this logic would check if it's 1 or not, if it's major than 1 or not throughout the code. So you can also see how the dynamic keys are actually being written, which they're communicated to the user. So by having this knowledge, you can introduce arbitrary functionality in the SMC component. You can use all the generic IOs which are connected somewhere in the system. Of course, for that, you need to debug a little more. But by having this knowledge, by having the SMC keys, by being able to query them, it also allows you a very nice way to debug your code. Because from the OS, you can query the keys, so you can put some debugging functionality for your custom firmware exposed through the SM keys, which is quite cool. And you can also, and this feedback is read-write, you can also write to the SMC, have some specific keys handled by your own functions, and then do functionality upon that. So we got from knowing nothing about this system, from having just an update from Apple, to ways which in IT are considered pretty convenient to have in order to do debugging. And then of course you can do this we showed for educational example only. So if you do this and you break the system, we do not pay for it, but it can be a great starting point for all of you that want to do evil deeds. I don't know what you want to do with SMC modification, or just to explore how this system works. But it's a classic example of an embedded subsystems which is not protected in a way, because the security hash is just, at the end, is just integrity verification. It is some piece of hardware which can be modified from the OS. It can be done from user space. It can be queried from user space. And then it taps on the system into different systems like the battery and so on. So it's a classic example of interesting, and it's fairly easy to do that. It was good for as an educational example in our case, and we hope you find it interesting. So we have no time left. This was our little presentation. We hope that, I know there was a lot of content. I know we spoke very fast. We hope that it was interesting to you to see these kind of things. If you have any questions, I think this time we have 5 minutes for questions. Otherwise, please ask now, or you can approach us later. We're always happy to discuss. Thank you.
Thank you very much. Questions? Don't be shy.
Don't be shy. I put a video in the meantime. This is the actual flashing of. Oops, it's gone.
Can you turn on the project?
This is the actual flashing of a modified SMC on the Mac. From the EFI shell, we execute the flasher, and that's a modified firmware being uploaded on the system. When you do that, the fan will go because the system tries to be conservative. So when you disable the SMC, the fans are always on at maximum speed. And as soon as the update stops, the fan goes down, the system reboots, and then you have your code on the system. Yes. So no questions?
Well, then thank you, Andrea and Daniele. Let's give them a big round of applause.